In the previous video, we managed to prove the triangle inequality in the case of complex numbers where a and b are complex. But we didn't really get the chance to explain what it really means. What does the triangle inequality say? How can we interpret this inequality over here? And in particular, why do we use the term triangle in the name? Well, in order to fully understand the triangle inequality, we first have to remember that we're dealing with complex numbers. And complex numbers are numbers that can be written in the form z equals x plus iy, where x is called the real part of the complex number z, and y is called the imaginary part of z. Most importantly, these complex numbers can be represented in a plane, where the x-axis represents the real part of z, and the y-axis represents the imaginary part of z. Now, it's important to remember that x and y are real numbers, and the only imaginary number is I, where I is equal to the square root of -1. FYI, the plane that represents the complex numbers is called the Argand diagram. Let's say, for example, that we have z equals 3 plus 2i. So 3 represents the real part of z, and if we say that 3 is over here in the real axis, and 2 is over here in the imaginary axis, well, we have z, which is placed over here. So essentially, the coordinates of z are defined by the real part and the imaginary part. We can say that z has coordinates of 3 on the so-called x-axis, the real part, and 2 on the y-axis, the imaginary part. And what's neat about this is that complex numbers can be sort of represented by vectors, since we are dealing with planes. And the coordinates of that vector is given by the real and imaginary part. And so it's crucial to note that when we talk about the magnitude of a complex number, we are essentially talking about the magnitude, and therefore the length, of a vector with the coordinates being the real and imaginary part of that complex number. So for example, here the vector u has coordinates 3 on the x-axis, the real part, and 2 on the y-axis. And so it's really key to remember the geometric interpretation of complex numbers. Now that we know all this, we can finally try to understand the meaning behind the triangle inequality. So we have two complex numbers, a and b, and they each represent a vector. So for example, for a complex number a, we have a vector u associated with it. So I'm drawing here the vector u. And similarly, for a complex number b, we have another vector associated with it, which I will call v. And when we talk about the modulus of our complex number a, we are essentially talking about the magnitude of the vector u, and similarly for b. But what would the modulus of a plus b represent? Well, remember that a represents, the vector u is represented by a, and similarly for b, which is represented by v, vector v. So we have the magnitude of u added with v, vector v. And the way we add two vectors from a geometrical standpoint is we add them end to end, just like this. And so the vector u plus v is the vector joining these two endpoints, which is this vector over here that I'm drawing in yellow. So this is the vector u plus v. And now we can readily interpret the triangle inequality. Essentially what it is saying is that the magnitude of the addition of the two vectors u and v will always be less than the length of the first vector u added with the length of the second vector v. And this makes sense because the straight line, so the line that joins the endpoints of the two vectors here, this straight line will always be the shortest distance in a plane. And therefore, the length, so the magnitude of this vector over here, will always be shorter or equal to the length of the first vector plus the length of the second vector. And there is only equality here if we have a sort of flat triangle. In other words, when the vectors u and v are parallel. Indeed, if the vectors u and v are parallel, then we have that the magnitude of u plus the magnitude of v is actually equal to the magnitude of u plus v, since these two vectors are parallel. Because in that case, to get the magnitude of the resulting vector, well, we just add the magnitudes of each individual vector. And so that is why we call this inequality the triangle inequality, because essentially what it is telling us is that any side, if we choose any side of a triangle, well, its length will always be less than the sum of the two other sides of the triangle. So in this case, we have this triangle over here, and the length of the side u plus v will always be less than the sum of the length of u and vector v. In conclusion, it's important to appreciate the geometrical interpretation of the triangle inequality, because it's important to remember that the triangle inequality involves complex numbers, and complex numbers can always be associated with vectors.